Hi, my name is Akshay and this is Half Sleeves. In the last video, we looked at the Python implementation of Gradient Descent Ascent, and we saw that even on the simple toy examples, GDA or Gradient Descent Ascent fails to converge to a minimax point. In this video, we will look at the Python code implementation of the condition which we discussed in the third video of this playlist. The link to the third video is in the description. This condition makes GANs converge to the correct minimax point by forcing both the critic and the generator to minimize the loss function, rather than one network minimizing and one maximizing the loss function. This condition is actually a loss function and it is called duality gap. The name duality gap is mentioned in the paper on which these videos are based. The link to the paper is in the description. The duality gap condition looks like this, and it can also be written like this. In this new form, we have just calculated the maximum value of x and minimum value of y and replaced it in the formula, where x star and y star are the maximum and the minimum values of x and y. As you can see here, there are two fixed values here in this formula, which is x star and y star, and also there are two free values in this formula, which is x and y. So we will be implementing this formula of duality gap in our code. We will be trying to find the values of x and y such that the absolute value of this final loss function is 0. Here in our code, we will implement this condition or duality gap on same toy examples like last video and show that this method converges to the correct minimax point in all the cases where the gradient descent ascent was not able to converge or was converging to wrong points. In this video, I'll use many coding concepts from the last video or the previous video. The link to the previous video is also in the description. The lines from 1 to 18 are just like the last video. So in line number 1 and 2, we will import the function grad and numpy from the library autograd. Next, in line 4 and 5, we will define our input x and y. In line 6, we define our learning rate, and in line 7, we define the variable named equation. This variable, which is named equation, will decide which first loss function we are minimizing. Here, all these loss functions are called as first loss functions because they are not the final loss functions. These first loss functions are used by duality gap to calculate the final loss. Duality gap is the main or the final loss function. In duality gap formula, this first loss function is shown by two variable function f. From line 10 to 17, we define three different first loss functions based on the value of the variable which is named equation. The name of this loss function will be func underscore or func underscore. In line 19, we define a function named dg, which stands for duality gap. This condition of duality gap is our second and final loss function, which in line 20, 21 and 22 uses the previously selected loss function to calculate the final loss which both the networks, critic and the generator will minimize. In line number 26 and 27, we create two nested loops, which in turn run for 500 iterations. That is, for each iteration in the first loop, the weights are updated 5 times. From line 29 to 32, we are calculating the partial derivatives of the first loss function with respect to x and y. The name of the partial derivatives are y underscore grad 1 and x underscore grad 1. In line 34 and 35, we update the weights with the help of the partial derivatives calculated earlier. That is, we maximize the first loss function on x-axis and we minimize the first loss function on y-axis. When we do that, we will get new x and y values, which we in our code will call y underscore min min underscore 1, which is y underscore min underscore 1, and x underscore max underscore 1. Actually, y underscore min underscore 1 and x underscore max underscore 1 are the x star and y star values in the formula which we are implementing in this code and which we are trying to minimize. From line 38 to 41, we again calculate the partial derivatives. But this time, we are calculating the partial derivatives of the final loss function or the duality gap. As you can see in the lines 19 to 23, that duality gap or the second loss function is nothing but the difference of the first loss functions, with y underscore min underscore 1 and x underscore max underscore 1 inside them, which is just like implementing this loss function. Now, since we have only one common loss function for both the networks, we can minimize both x as well as y. In the lines 43 to 45, we take the partial derivatives of the final loss function or duality gap and subtract from the current x and y and get the new x and y. In line 47, we just print the z, x and y values. If we run this cell, we will get the values for z, x and y. Remember that the variable which is named equation in this cell is 0, which means that we have this as the loss function and the correct minimax point is at 0. And indeed, our x and y converge to 0, 0, as you can look in the output of x and y values. Now let's change that variable which is named equation in this cell to 1, which means that now we have this as our loss function and the correct minimax point is not at 0, 0. And indeed, our x and y values diverge away from 0, 0. Now let's change that variable which is named equation in this cell to 2, which means that now we have this as our loss function and the correct minimax point is again at 0, 0. And indeed, our x and y converge to 0, 0, as you can see here. So this is how you can improve your GANs by implementing this duality gap loss function in them. And finally, thank you for watching this series of videos on fixing GANs. The complete list of playlists and previous videos is also in the description.